Okay, class, so chapter 4 talks about some different areas of graph theory. Feel free to read the entire chapter. We're just going to be focusing on sections 1, 2, and 5. So let's start with section 1, which is an introduction to graph theory. Keep in mind this is a lot of definitions. I've included a glossary in the PowerPoint, but there's also one at the back of section 4.1 in our text. So what is a graph? Well, a graph is a graph can be represented as a picture, right? And these are going to be pictures of drawings with dots and lines. So these dots are called our vertices and our lines are called edges. So here this one has 3 vertices and 2 edges. Here this graph has 2 vertices and 1 edge. And all of these are different types of graphs that we're going to be talking about as we go through this section. So the formal definition of a graph is this. A graph is an ordered pair, G, consisting of a non-empty set V of vertices and a set of edges, okay? And these are 2-element subsets of V. Well, what does that mean? Let's go ahead and graph an example. So here I have my graph. Its vertices are A, B, C, D, E. And its edges, as you can see, are ordered pairs of 2 elements of V. We could also define this as G, where my first group is my set of vertices, and then my second set is my set of edges. So here are my vertices, and here are my edges. So why don't we go ahead and draw this? So I have vertices A, B, C, D, E. Why am I drawing it like that? Well, why don't I show you? So in here I have A goes to B, A goes to C, this is C, A goes to E, B goes to D, B goes to E, and C goes to D. So I've got a nice little house. But note, it could be drawn another way. I could have put E in the middle. A, B, E, C, D. And it would have been the exact same graph, just I moved that E point around. So be careful with how you draw a graph. Now, one thing we like to be able to look at is whether or not graphs are equal. So why don't we check below to see whether the graphs are equal. So my first graph, G1, has the points A, B, C, E, but I have A going to B, and then B going to C. My second graph is I have A going to C. Maybe I shouldn't use blue with a blue background, guys. Sorry. So I have A going to C, and then C going to B. Now these graphs look the same, but they're not equal. They're not equal because, and I'll tell you why, because AB does not equal AC, okay? BC, CB, they're the same thing, but AB doesn't equal AC. But because they look the same, they basically are the same because these are isomorphic, and we're going to talk about that in the next slide. And isomorphism is a big topic when it comes to higher level algebra courses and topology. So it's nice to have a good visual representation of what something is, or what 2 things look like when they are isomorphic. So graphs are isomorphic if they are the same except for the names of their vertices, right? We could say that these graphs are the same, but their names of their vertices are different. So in order to make renaming vertices precise, we use the following definition. So here's the formal definition of an isomorphism. Is that an isomorphism between 2 graphs is a bijection. Friendly reminder, a bijection is a function that is 1-to-1 and onto. From the vertices of our first graph to the vertices of our second graph, such that AB is an edge in G1 only if F of AB, F of B is an edge in G2. Okay? when two graphs are isomorphic, we write it like this. Okay, so let's go ahead and work through an example. We need to decide whether the graphs G1 and G2 are equal or isomorphic. So the first thing I need to check is whether these two graphs are equal. So let's take a look at their edges, right? What are their edges named? AB, okay. AC, okay. CD, okay. Here's where we have an issue, okay? These are not equal because AD doesn't equal BC. Next, I can check if they're isomorphic. So the first thing I might want to do is sketch these guys out. So I have A, and A goes to B, and A goes to C, and A goes to D. Okay, so if I have A, D, B, C, I have for this graph G1, A goes to B, A goes to C, A goes to D, but then C also goes to D. Beautiful, so there's my graph. Then for my next graph, we'll label our points in the same order. A, D, B, C. I have A goes to B, A goes to C, B goes to C, and then C, AB, AC, BC, oh, there's no AD. That's where I made my mistake. There's no AD. And then DC. Now, okay, here we have, right? These graphs look the same, right? If I was to put C in A's place, right? So if I was to rotate this, right, then I'd have C if I was to not rotate it, but say like flip it, right, I'd have C, B, A, D, right? And then this definitely looks like an isomorphic, right? We'll flip it along the horizontal axis. So what I need to do now is I need to build a bijection. Okay, I have to build a bijection. So let's name that bijection G. And I should probably make myself some more room. So how am I going to build that bijection? Remembering that I need to flip along a vertical axis. Okay. So what I want is I'm going to define this to go from V1 to V2. I want G of A to go to C, right? Because we're flipping it vertically. I want G of B to go to D, right? I want G of B to go to D. Oh, I already did that. G of D to go to B. And then I need G of C to go to A. So our edges in G1, which are AB, AC, AD, and CD, under this new isomorphism, right, I've got G of A, comma, G of B, dot, 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 all the way down to our last one, which is G of C, G of D. And you can see that that's going to give me, right, G of A is C, G of B is D. Next, I have G of C is A, G of D is B. This becomes G2. So G1 is isomorphic to G2. An isomorphism class is a collection of isomorphic graphs. We also can care about the subgraphs of larger graphs. So given that I have a graph G prime, it's a subgraph of G, provided that V prime is a subgraph of V, and E prime is a subgraph of E. So let's take a look at this right here. Right here we have, this is actually K sub 6. We're going to talk about that in a couple of slides. It has this subgraph, which can be found right here. We also say that G prime equals V prime is an induced subgraph, provided V prime is contained in E, and for every edge whose vertices are in V prime, it's also an edge in E prime. So this is induced. I.e., what does that mean? Every edge that connects the vertices in the graph is also in the subgraph. So this is connected. Every vertices that connect these edges in the subgraph is also connected. A graph is simple, and so far all the graphs we've been looking at so far are simple. That means that no set of vertices are connected more than once, right? This makes sense because we define our edges as sets, and no set can contain duplicate elements. It would look like this, right? I have two ABs. Well, you wouldn't want to write that in a set theory, so we don't do that. Take that away. A graph that's not simple is called a multigraph, right? Multisets can contain and their edges define a multiset. Multisets can contain a single element multiple times. So this would be the graph where I have the set AB, AB. But that just doesn't feel natural because that's not what we learned in set theory. So I wasn't worried about multigraphs too much in your case. A graph is connected, and so far all the graphs we've been looking at is connected. And that means you can go between any 2 points following a path of edges. So these graphs are not connected because there's no way for me to get to A to B. Now I can't change directions, as tempting as that is. You can't do that. You have to follow by path. We call a graph complete if there are all possible edges between every vertices. So we call these K sub n graphs, and K sub n graphs have degree 1. So remember, the degree of a vertices is the number of edges touching it. So here I have K2. I have all possible edges there. K3, all possible edges. K4, right? These all have degree of 3. K5, these all have degree of 4. K6, these all have degree of 5. So every possible vertices is connected to every other vertices, and that's what makes it complete. The handshake lemma is that for any graph, the sum of degrees of vertices in the graph is always twice the number of edges. So let's repeat that again. In any graph, the sum of the number of degrees in the vertices is always twice the number of edges. This is also sometimes called the degree sum formula. And that makes sense, right? Here I have one edge, but I have two vertices, so it's a 2-to-1 ratio. Here I have 3 edges and 3 vertices. In any graph, the sum of the degrees of the vertices is always twice the number of edges. So here I have degree 6 divided by 2, that gives me 3, so that's my 3 vertices. So it's the sum of the degrees. In this one example, each of these has degree 1. 1 plus 1 is 2. 1 divided by 2 is 1, so they've got one edge. So a proposition of this is, in any graph, the number of vertices with odd degree must be even. So suppose that there was a graph with an odd number of vertices of odd degree. So then the sum of the degrees would be odd, which is impossible by the handshake lemma. Bipartite graphs are graphs that can be broken up into 2 subsets. So let's talk about this. So 2 vertices are adjacent if they're connected by an edge. So in this case, A1 is adjacent to B1, B2, and B4. A graph is bipartite if the vertices can be divided into two sets with no vertices in A adjacent and no vertices in B adjacent. So if I did this, then the subset of A would not be adjacent, would not be bipartite because A is connected to the other A's. Same thing if I did the same thing here in B. Let's clear that. So if each vertex in A is adjacent to all the vertices in B, then the graph is a complete bipartite graph, and that gets the special name. So this is the, this would be if I had a path here, and this one only goes to this through, it needs to go to these, and this one needs to go to this one, and this one needs to go to this one. So now it's complete. And we write this case of 4, 4. That's an example of a named graph. So Kn is the complete graph on n vertices. M, n is the complete graph on m and n vertices. Cn is the cycle on n vertices. It's always just one big loop. And Pn is the path on n plus 1 vertices. So n edges. So you just take one long path. So that it's nice to remember, like for the rest of the n, these are defined by their vertices. This one, it's defined by its edges, defined by number of edges. Don't forget. Here's a glossary included of all the definitions. They are also found in your online text at the end of section 4.1, but I thought it might be nice to have them all in one space.